Hi, I'm Shamali Chatterjee. I lead ICAN, that is the Innovatory for Cells and Neural Machines, and I will give you a snapshot of IoT and on-device computation for digital agriculture. Okay, so we will talk about light bandwidth workloads, and we will talk about heavy bandwidth workloads that are very relevant to digital agriculture. So for the first one, we have outlier or anomaly detection for measuring sensor health. And for the second one, for the heavier bandwidth workloads, we have object detection. The motivation for doing on-device computation, so on-device as opposed to offloading everything to the cloud, is one, we want to decrease the latency and pressure on network bandwidth. Two, we want to decrease cost. And three, increase security, privacy, etc. I will also show you some test deployments of a cyber physical system consisting of sensors for moisture and for temperature connected to the edge device, which is a Raspberry Pi. For the specific algorithm that we are using is anomaly detection. And then we are also using an object detection algorithm using an NVIDIA-Jetson. And I will show you some sensor deployments that have been done via the WIN project, which is the Wabash Heartland Innovation Network project. So the ingredients of a smart farm, right? This is from the FarmBeats paper from NSDI 2017. FarmBeats is an IoT platform for data-driven agriculture. And this was motivated by the large number of data streams from ubiquitous and oftentimes inexpensive sensors that are deployed in the farm for things such as soil, moisture, pH, etc. Right? And then you have networking using LoRa and BLE. And then you also have the cloud platform for long-term storage and analytics. So this is at a high level what an IoT platform for digital agriculture will look like. Now, the first little algorithm snapshot that I'll give you is on anomaly detection. Anomaly detection is essentially an algorithm that detects rare events by the fact that these events differ significantly from the majority of the data, and they are effective for detecting sensor health, and in other cases it might also tell you if there is a malicious attack on the sensor because of which the sensor is malfunctioning. Examples of these data streams in the digital agriculture setting come from moisture, temperature, nitrate. They might also be microbiome soil sensors. Now we have an example deployment from our lab here at this link, which is an anomaly detection for temperature and humidity sensors that are actually also deployed in the farms, just to show you how the anomaly detection works. So like I said, anomaly detection algorithms, they detect anomalies, but we want this detection to happen close to the source of the data. So this is resource efficient. But the challenges are you have these multimodal data streams coming from multiple sensors. Now, our approach is the simpler variant of an algorithm. It is called ARIMA, which is auto-regressive integrated moving average. And the more sophisticated variant of an anomaly detection algorithm would be an LSTM, which is also computationally more expensive. We see that this ARIMA model, which is represented as a function ARIMA PDQ, where P is the number of lag observations included in the regression model. And then we have D and Q. D is the differencing and Q is the time window. So we optimize these hyperparameters for the ARIMA model and we run it. And essentially what we're doing is we're checking for sensor malfunctioning, and we're also seeing if we need to update the model, right? Because there is something called model decay or concept drift that you see in the bottom right, because of which the model may need to be updated from time to time. So this is essentially what the three parameters of the ARIMA model are. We have optimized the three parameters, and then we use ARIMA for time forecasting. We see that the mean squared error is 0.124 for our model. We test using the first 30% samples and train rather train using the first 30% samples and test using 70%, and then we tune the model online during the testing phase. Our goal is to reduce the data transfer from the sensor node to the server, and we do this essentially using time series forecasting, and we change the error tolerance in order to decrease the data that is sent from the sensor node to the server. So in this case, we see that the error tolerance is 0, and so 100% of the data is sent from the sensor node to the server. You have the true value in green here. In black, you have the predicted value using REMA. In blue, you have the data that is sent, and there is no data that is not sent in this case. So there are no red dots here. So in here, you see that the data sent is now 63.82% when the error tolerance is increased to 0.10. So now some of the data is being sent to the server. Here we see that the data sent is decreasing further because we have increased the error tolerance to 0.20. So now the data sent has decreased from 60-something to 50-something. And finally, here we see as the error tolerance is increased to 3, the data sent has drastically reduced to 7.44%, which is essentially our goal, to have okay error tolerance so that not a lot of the data is being sent to the server. Now, here what you see is a snapshot of the data sent. On the y-axis, there is a second y-axis that gives you the mean squared error, and on the x-axis, you have the error tolerance. So we see that as the error tolerance is increasing, the mean squared error of the model is increasing, but the data sent from the sensor to the server is decreasing. So the second snapshot is a heavier bandwidth snapshot, and for this we have object detection. Now, object detection is done in the digital agriculture setting. For example, if you have these drone imagery, so you don't want to send all the data to the cloud. So only when there is some exceptional event that is detected, then you communicate this to the gateway node, because object detection is a resource-intensive machine learning task. And what we use here is a convolutional neural network, specifically a convolutional neural network that is good in terms of architecture, meaning it has a lesser number of parameters than a regular CNN or convolutional neural network, and the variant is a faster RCNN. You can see a preview of more details of the algorithm. We call it ApproxNet at this link. But essentially what happens is, because we are using an approximate version of the convolutional neural net, we are exiting early. So we're not going all the way through the neural network. We do early exit for approximation. And the reason we do this is because bandwidth to the cloud is expensive. Processing on the cloud could also be expensive, so you want to use the edge servers that are there at the farm, and a centralized solution can oftentimes not scale up as you have these ubiquitous data streams. So most of the video analytics queries, they involve inferencing over continents, and this is a very compute-intensive task. And these are generally too slow on edge devices to keep up with the live video stream rate, which is 30 frames per second, or they're very memory heavy. And that's how you need approximate versions of these solutions. So this is what our sensor node looks like. That HDC 2010 is our sensor. So this is an example of this embedded board with a temperature and a humidity sensor. And then you also saw the LoRa connection, the antenna at the top of the board. And these are embedded devices that we have used. For the first one is the one that is used for anomaly detection. It's a Raspberry Pi node. It does not have a GPU, and it's much less expensive, whereas an NVIDIA-Jetson TX2 is more expensive and has a GPU backend, and this is what we use for object detection. Now, for object detection, we have to approximate the convolutional neural network. There are 3 ways of approximation that we use. We downsample the image size, and then we do early exit from the continent. And the third thing that we do is we change the number of region proposals that the faster RCNN model makes. And I encourage you to go to the link to understand a little more of the faster RCNN structure or architecture. This is an example of the deployment at Purdue. There are 13 nodes deployed throughout Purdue, sensor, collector, and gateway nodes. And we see in general, the PDR, that is the packet delivery rate, is high. There are some lossy nodes, but in general, it's pretty good. Here we see the TPAC, which is an experimental form at Purdue, deployment of a wireless mesh network. And here we have two kinds of networking. We have the long-range LoRa and the short-range BLE communication. And finally, these are some examples of these sensor nodes. You have a temperature and humidity sensor node, and here how the sensor is connected through a wire to the embedded board, which is outside the soil. Thank you.